So does the fact that that load we already proved to ourselves is 2/3 of the way over, the single load, if I was to replace this with a single load? And then what do I do to calculate that load? Well, last time it was that single load was equal to 420 pounds per foot times the fact that this thing is 24 feet long. So the feet cancel and that gives us pounds. Why does that not give us the right answer in this case though? Well, because it's only 420 on one side. It actually goes to 0 on the other side. So it's actually the average of 420 and 0. So for that reason, kind of like the area of a triangle, I've really got to cut that in half. I mean, the average of 420 and 0 is 210. So if we took 210 times 24, we can sort of think of it as just a distributed load, but really it's kind of like the area of a triangle. So anyway, all that to say, we would actually get a force of 5,040. Notice the units take care of themselves. It really is pounds. And so it is actually important that 420 is pounds per foot. That might bother you a little bit. I mean, it did me for a while. That's not 420 pounds. Well, it is 420 pounds right there at the end, but it's per foot. So every single foot would have 420 pounds. But then as you move to the left, then it gets less and less and less. So, okay, I found this thing. It's 50-40. It's aiming at that spot right there, 1/3 of the way in. And now I don't have infinite mini loads. I just have one. And so I'm kind of on my way. And so let's draw a free body diagram of that just to clean it up a little bit. In one respect, the argument could be made that you don't need one. But of course, if I'm going to draw that free body diagram, aren't I going to need how much of that force is there and there? So collectively, I'll just call these force at A and force at B. Collectively, those two forces are going to have to add up to 50-40 to keep this thing, to keep the sum of the forces in Y 0, but it's not in the middle this time. That's what's complicated. Can you appreciate that based on the location of 50-40, force B is going to do more of the work? Going to do more of the work. And so I, in a sense, don't have a choice here, but to do a sum of the moments calculation to see how much of it is over there at B. So I could say, well, the sum of the moments, feeling the need to change color, the sum of the moments, I don't know, around A or B, doesn't really matter, I guess. I'll just do A. That would be force B times its distance of A of 24 feet. And that'd be in the positive direction since that's counterclockwise, but then 50-40 is trying to get it to go clockwise. So that'd actually be minus. And here's where, for the first time, it's important to understand that that's 2/3 of the way over. So that was nice that I made it 24 because 2/3 of 24 is 16. So that means it's 16 feet away, and that's it. Force of A contributes nothing to the sum of the moments because it's pointing at A, it has no distance. And so if I set all of that equal to 0, I get force of B is 3,360 pounds. And now I could do, and I won't write this down, but the sum of the forces in Y. So if I went 50-40 minus 3,360, that'd give me the force at A. So I think I'll just write it in here, which is 1680. So indeed, they are both working together to be 5,040 pounds, but force B, as predicted, would be larger. As a shortcut, here's just a question that occurs to me. As a shortcut, does 3,360 also happen to be 2/3 of 50-40? In other words, did I actually have to do the sum of the moments calculation? Since it was 2/3 of the way over there, is it 2/3 of the force? I actually think the answer to that is yes, although off the top of my head, I'm not sure. If you take 3,360 divided by 50-40, is it 0.66666? So again, if I was doing this all the time, like that might be something I would want to know as a shortcut and so forth, because that'd save me some trouble. And so in a sense, now I'm actually ready for a free body diagram because I've actually reduced this mess to just some forces. And let's see, should I switch to the right side here or is that foolish? I think it's foolish. Hey, Thomas, you got a bunch of homework over there. Don't forget it before you leave. So I think I'll stick with the left side of this for my free body diagram. So I've got this beam. And I mentioned this to you guys the other day, but like this is the symbol for I'm breaking the beam. There's more over there. So in the end, what I needed was actually force A, 1680. And we said by convention that the rest of the beam that's connected to this is providing a force vertically. Force vertically is so important in engineering. We said, instead of just calling it vertical force, we said V for shear. And by the way, that's the first time this ever occurred to me, but maybe V is vertical. Maybe that's why somebody picked V, because shear is vertical.
There was a lot of speculation online, but no one had like a solid answer.
Oh, really? Interesting. Thanks for telling us that. I didn't know. And then by convention, we said, let's have the moment be positive here or counterclockwise. And then what am I missing? I think I have everything except for what?
Your 50-40. Yeah, 50-40 force.
Notice the 50-40 force, though, isn't in the picture until you make it 16 feet over. Isn't that weird? So if we said, let's go over a distance of X, as we did the other day, where X is any number we want, 50-40 doesn't make it into the picture until later. And so here's what makes these kind of tricky. Does that mean there's no force up there? No, there's still force up there, but it's like just a tinier chunk of the triangle. And so what's that? What do I call that? Because notice 420 is not in the picture. It's clear over to the right, and unless X is 24 feet, then it's not in there. So the other day, you may remember when it was vertical, we had a bunch of arrows across the top of it, and because it was level all the way across, we said, oh, it's okay, that's fine, it's 312 pounds per foot. Like we actually know the answer to that. But here, what are we supposed to say, considering we don't actually know where we are? Well, this is why we've actually got to come up with an equation. Before there wasn't an equation, it was just 312 every place you go. But now we kind of need to know, well, the same thing we knew over here, which is that longest height. We actually need a name for that. But we aren't going to know that unless we have some kind of an equation. So see if this makes sense to you. There's more than one way to do this, but does it make sense if I look at the kind of the larger triangle up here, that I could say 420 for the entire height divided by 24 would be the proportion of, well, height to width. And isn't this triangle the same triangle, just smaller? It's like a similar triangle, it's proportionate. So if I say 420 is to this distance, what this is to this distance, wouldn't those be equal to each other? See the logic in that? So think of it as, I'm over here. That's the triangle that I have drawn. So aren't those two triangles proportionate? This height would be to this length, what this height would be to this length. And effectively, that's what tangent says, right? Tangent is opposite over adjacent. It's the same angle, no matter which triangle you're looking at. So if I kept going then and looked at that smaller triangle, it would be, well, something over X. Since my distance down here is X, at least I gave it a name. It's not really helpful, but I gave it X. And then this height right here, I don't know what to call that. For now, I'm just going to call it I don't know what to call it. I'm gonna call it question mark, whatever that height is.
Wouldn't it be maybe not a slope, but like equation?
Yeah, it's kind of like slope. So that's the other way to look at this. Isn't that a line, y equals mx plus b? We could take that approach too, and we'll talk about that in a second. So I guess I could say if I wanted to solve this for that question mark, then that if I multiplied my x to the other side, then I'd have 420x over 24. Maybe I'm lucky and that simplifies to some nicer fraction, or maybe I just say, well, I want a decimal. I don't really care. 420 divided by 24. Well, it is a terminating decimal, 17.5. So now I have a name for that. In other words, what's the height of your triangle? Well, it totally depends on x. It's 1.75 times wherever you're located. So in a sense, I have a name for that now. 17.5 times x. And again, that's pounds per foot. Now, to your kind of comment, Connor, about slope, like isn't the slope of the equation of a line y equals mx plus b, and if I put the y-intercept right there, so it has a y-intercept of 0, then all I need y equals mx plus nothing, since I set the axis in a place that was nice for myself, then all I need is the slope. Well, isn't the rise 420 and the run 24? So it's 420 over 24. Hey, it's the same thing we just got over here. So you could actually take either approach. So you're literally finding an equation for that distance up there. And now we have it. And then just to check and see if it works, does it make sense if you stuck in 24 into this? If I stuck 24 into there for x, shouldn't I get 420 out? That would be kind of checking to see if it's working. Or logically, if 420 is the sort of the height here, if I went to the middle when x is 12, shouldn't this be half of 420, which is 210? So if I put 12 in for x, I should get 210 for my height. So, take a little bit of time to realize, hey, this is working. Like it's actually telling me the height depending on where I am with x. And so this calculation is no joke and very important. Now, armed with that, what did we just do a second ago? What did we just do a second ago to replace all of these millions of arrows with just one? Didn't we take 420 times 24 and then divide by 2, and that gave us the 50/40? Well, is it any different here? No. So to get one force as above, I take 17.5x and multiply it by the distance across, which is x, and then times a half. Again, identical to what we did up here. Except for this time, I get, well, kind of an equation. Half of 17.5 is 8.75. I'd rather write that than 17.5 over 2. I just want one number. And then I have x times x. And so that's actually my single force now. Now, again, it depends on where x is. It's not a number because it depends what x is as to what that number is. Again, out of interest, if I plugged in x is 24 here, I should get 50/40, shouldn't I? So if x is all the way across this thing, a second ago we got 50/40 for this. What we have here is a formula that tells us that no matter what the length is. That's kind of cool. And there's not a way around this. Like this is complicated and surprising and painful. Okay, so if that's the case, then I kind of feel like I should modify my free body diagram and not have all of those arrows anymore. So what would my free body diagram look like now? Almost used up a whole page and we got started. So now I can stick in that force. So that force would still be 2/3 of the way over, but it'd be 8.75 x squared. And maybe I should write its location in there. It's 2/3 of the way over from x. So still point A. Now I basically have my free body diagram. So let me move this more. It's okay up above. So now this has got everything in it. It's got my one single force, 8.75 x squared. It's 2/3 of the way in. It's got V, it's got M, it's got the original 1680. And now I've got everything I need to, well, start calculating the shear in the moment. So let's tackle the shear first. So shear, as you know, is nothing more than just the sum of the forces in Y, which of course need to be 0. Maybe V is vertical. So then I look at this and say, okay, cool. What are the sum of the forces in Y? And I can see that I got 1680 going up. I've got V going down. And M for moment isn't up or down. It's rotational, so it's not part of it. And then don't I have minus 8.75 x squared going down? That's it, isn't it? And we know those better be 0 or the beam is moving up and down. So if I solve this for V, by adding V to the other side, then don't I have 1680 minus 8.75 x squared for my shear equation? Again, why is it an equation? Because the shear on the beam depends on where you are. And this is basically saying, yeah, do you know what the shear is? Well, you got to tell me X and then I can tell you. It's kind of like in the language of algebra function notation. It's kind of like going back and saying, oh, did you know the shear is a function of X? And then on the other side, you see numbers and X's. And so that's kind of cool. Now, notice when you graph this, like, oh, that's interesting. That is a parabola. The shear equation is a parabola. And remember, the reason we're graphing this is because there's literally millions of different shears, and the graph will tell us which one is the biggest. All we really care about is which one is the biggest, but that's why we got to make a diagram. Well, if you're really good at calculus, do you need to draw this out to find the maximum? No. From Calc 1, the maximum happens when the derivative is equal to 0. Now you do have to be careful though, because remember calculus setting the slope equal to 0 also finds minimums or maximums, and you can't tell the difference. So there is a bit of an advantage to a diagram for that, which is kind of cool. And I do want a rough sketch of this. Now I would expect on a test that you would just type this in your graphing calculator and use that to kind of analyze it to get a decent graph of it. Because the main thing is to kind of, like, maybe you can tell, like Tristan said last time, because it's negative x squared, that this parabola is actually going like this. And so I find myself thinking, oh, it's at the top. Like it's up there at the top. This, because it's a parabola, actually doesn't have a minimum. And so this won't be terrible. It'll be like it'd be at the top of a parabola. However, you might stick this one in your graphing calculator. And remember, this only lives between 0 and 24. Let's add that to our notes. Doesn't x have to stay between 0 and 24 in order to actually represent our beam? And so if you graph this and set your window from 0 to 24, you're not going to see the parabola you think you're going to see. So I would like you to take the time to do this. Seems like a relatively good test question. We'll see. Maybe it'll either be a rectangular one or a triangular one like this. 1680 minus 8.75 x squared. If you just hit zoom, you probably won't see the graph because you have really large values here. Like it should take you some time to find it. What happened? What did it say? Come show me really quick, because it's probably just something, either some setting on your calculator, or maybe you typed something in wrong. There's nothing wrong with that. Oh, I think it's probably that negative in Y4. There's like nothing there. Tell me if that doesn't fix it. There's nothing wrong with what you typed. So I'm going into window and setting my X minimum to 0, my X maximum. Does that fix it?
Yeah.
And then I don't know what to set my Y max at, but notice if you stare at this equation, if you put 0 in for X, you get 1680. So that means you better go up. I'm going to go up to 2000. So I'm going to say from 0 to 2000 and see what I get. I'll erase this, but here's what I see so far. And I definitely am only showing 0 to 24. And I'm seeing something that does this. Now, does it make sense? You got to see all the way to 24 though. So that means this keeps on going down. So that means I need a negative window as well. So I can't go from 0 to 2000. I'll try negative 2000 to 2000. And so mine still didn't make it to the end. So I have to even go down further. So I'm just kind of guessing and checking. And by the way, there's a faster way to know this. Like if you put 0 in for X, don't you get 1680? So it's like, that's why I knew the top, where the top was. Well, couldn't you put in 24 for X and see how far down that goes? Like you don't have to just sit here like an idiot guessing and checking like I'm doing. So I am going to get out of this because I'm realizing I'm wasting my time. 1680 minus 8.75 times 24 squared. Oh, that goes down to negative 3360. Before it kind of hits. And so what you thought you were going to see maybe was just kind of like a parabola. And it's like, oh, right there, there's the maximum. And we do see a parabola, but it turns out like we're seeing the right half of it. Does that make sense? So this is actually the peak of it, and then the rest of it is kind of over here. So this is a really interesting question, by the way, because if we had done calculus on it, it would have given us that answer up there, because that's the only place where that graph is 0 slope. And so we would have said the shear is 1680, but 3360 is bigger. We'd have got it wrong. Now, does it matter if it's negative or positive? No, it's a question of direction. You know, is it like right side going up or right side going down? So it doesn't make any difference. It's just what's the force that's causing this thing to shear. So do you see how, in a sense, calculus wouldn't have worked here? So that's why a shear, and even if it did, a shear diagram, the diagram where you actually see all of the different answers is kind of cool to look at, just to kind of see it, sort of check your work, make sure you're visualizing things. Remember, you can't be wrong in this career. So
this makes sense because we have that triangular load. Like I suspected the shear was going to be over there on the heavier side, but why is it? I don't understand why the graph is showing this. Like, I would have said 1680 even with that intuition. I'd have been like, I don't know why it's not giving me that answer. Why is it negative?
yeah, it's a good question. So because there's more load on the right, just like we discovered, and by the way, is it a coincidence that we just got those exact two answers right there? Like that was the load at each one of them. And as I was saying in class the other day, that's where the shear is going to happen because that's where the largest force is. So the fact that one side was 3360 and the other was 180, it does make sense conceptually that the largest shear is going to be on the right side of this because that's where more force is, which I think is rather interesting. Overall, I would say it's irrelevant that one is positive, one is negative. But again, that's the sign convention thing. In other words, you still wouldn't report that the shear is negative. You just say it is positive. So that's why somebody thought it'd be worth kind of messing around with that. So that's kind of an interesting graph. So V max, which I don't think you're being asked in here. I don't think I'll even ask it on the test. The reason you do this is to discover the V max. But all you have to do is kind of create the shear diagram so that you can determine that. So again, it's not obvious because 1680 is still the maximum if you actually count these as positive as negatives, because negative 300 or negative 3000 is not a big number. It's a tiny number. Remember, there's no such thing as negative numbers. Negative numbers are just directional. This is basically 3360 down instead of 3360 up, so to speak, but it's still causing shear.
So you don't believe in subtraction.
That's right. There's no such thing as subtraction or negative numbers.
Was that like, I tried saying that to someone, but they looked at me funny.
Yeah, say it to a math teacher, see what they come up with. They will struggle with that. You have to think your arguments through. But again, wouldn't Desmos make a nicer graph here? I feel free to go into Desmos and just graph this in Desmos and even take a screenshot of it, like for your homework. Like, don't do this stuff by hand. Do it on your graphing calculator and just make a rough, ugly sketch if that's easier. Do it in Desmos and copy it, whatever. I mean, that's way nicer. There's actually one more piece of information, though, that's on this graph that we haven't really taken advantage of yet. And we don't need it right now, but we will in just a second. So I'm going to go back and maybe draw this a little bit nicer. At least one kind of long, smooth curve. And that is this location right here. Do you agree that that's the place where the shear is actually nothing? Which is kind of weird, isn't it? I mean, there's actually no shear on the beam at that location. And oddly, it's not in the middle. It's not, and it was with the rectangular load last week. It was right in the middle, but this is not in the middle. And my drawing is pretty decent here because it shows it's a little bit to the right. You should be able to algebraically and just cheat on your calculator to locate that. Because if shear is 0, then couldn't you, well, go up to this equation up here and set it equal to 0, which would mean 8.75 x squared would have to equal 1680 since I set v equal to 0. So then if I divide by 8.75 and square root, wouldn't I be able to get that algebraically? It's just kind of fun to notice you don't have to be dependent on the machines. I got 192 for x squared. That came out even. That's kind of nice. So then if I take the square root of that, I got, oh, that's interesting. I got what mathematicians call an irrational number. I got a non-ratioable number. So I got like 13.86. Again, I don't care how you get that. Cheat on your calculator. You may remember under the calculate button, there's a function called 0. 0 is code for x-intercept or 0 for y, and you could just trace and get your calculator to spit that out to you. But this particular equation was algebraically not too difficult for us to figure out. But notice I basically have the 3 important points on this written down. I mean, since the graph shows that point has x is 24, and now I can see y is negative 3360, and the same for the other point. It's on the y-axis, so I know where it is there. And it's kind of labeled. So you would need these labels because as I said, the only reason anybody's going to look at this is for these 3 values, this one, and this one.
What is next square representative? The one and the 2, or is that just on its way to explaining the x-intercept?
Yeah, it was just on its way to x. So that's me just going back here and saying, oh, when is v equal to 0? Oh, okay, I can set this equal to 0 and solve it. So I was able to algebraically locate that point, which is kind of a source of cool. Now, true to what I said yesterday, which is actually I'm just kind of teaching you all of shear moment diagrams at once. Do you remember that we said if you took, there was like a derivative integral connection between all of these different formulas? So just a little side note here. we had our weight formula, which was 17.5x. That was our equation of that line that basically told us what the force would be, our weight would be, depending on what x was, right? And now we just got v, which is 1680 minus 8.75x squared. Now, technically, this weight right here, was it not aiming down, not up? So if I was to be technical about it, I would really throw a negative sign in there. What happens if you take the derivative of that shear expression? What's the derivative of 1680? Nothing. What's the derivative of 8.75x squared? Negative 17.5x. So in a sense, two things could be said here. I could say that W will equal V prime, right? Or I could say, if I took the integral of both sides of that equation, couldn't I also say the integral of W would be equal to V? Now, what's interesting about that is, if you take the integral of negative 17.5x, doesn't the x grow an exponent? And then you divide by 2. And so sure enough, you get negative 8.75x squared, but plus c, right? When you take an integral, there could have been a constant there, right? And it turns out the constant is 1680. It's like, if you don't do that, then this doesn't work. But it does grow a constant when you take an integral. And so, you know, in the end, the question would just be, well, okay, so this is v, but then what's v of 0? In other words, how do I figure out what that constant is? And in our situation back here, when x was 0, that means we're at the start, right? We're over there at the left. Well, what was the shear over there at the left-hand side? Wasn't it 1680? Like, you could actually do this entirely with calculus. We never even had to draw these pictures. I mean, isn't that just kind of crazy? And by the way, I'm kind of studying my way through strength of materials in the very last chapter. I just discovered this yesterday. The very last chapter that we're covering is covering exactly this. So you get to see this again. I told you you'd see it in the future. I just didn't think I'd be the one showing it to you. I thought it'd be like in one of your 300 level classes or something. But this is so important that it shows up more than once. My actual guess is that we'll be talking about it a little bit at the end of next semester, but then you'll probably still see it yet again later on, because I just showed you the beam calculation deal, and it was like, that was the main plain thing that you do. And so this is not something that you can be an engineer and not know. So again, wow, that is unbelievable. The way I like to think of though is just checking your work, because I kind of enjoy the process of just figuring it out mechanically and drawing pictures and saying some of the moments and some of the forces and why, and kind of, and then just saying afterwards, hey, let's take the derivative and make sure I didn't get it wrong. Look at that, I didn't get it wrong. And I catch genuinely lots of my own personal mistakes with that technique. So this is kind of cool. So in a sense, another person could kind of write it like this. I'm going to erase this because it's going to get too crowded, but it's like, you go this way by taking integrals, and you go this way by taking derivatives. In a sense, you kind of work your way up and downhill. So there's some deep magic with derivatives. And I remember showing when I teach calculus, maybe you've seen this before, but the volume of a sphere is 4/3 pi r cubed. Perhaps that at least rings a bell in your memory somewhere. The surface area of a sphere is 4 pi r squared. Most of my life, it's like, hey, 2 formulas, thank you. That's really cool that you did that. But if you take the derivative of this one, you get that one. This is 3D. This is 2D. When you take a derivative, you're actually moving down a dimension in the universe. Like, it's a very deep magic. It's not just, hey, I found the slope of this curve. I mean, that's cool too, of course, but but you're literally moving from one dimension to the other. Well, isn't that what we're doing here? If you move from weight to weight, which is actually pounds per foot, and we move to volume, I'm sorry, shear, which is actually just feet, I'm sorry, pounds. In a sense, I won't belabor this point, but in a sense, we're changing dimensions. Well, didn't those dimensions change? I mean, here it's 3D to, here it's 3D to 2D, but again, this is amazing, and calculus is much deeper than just kind of surviving book problems and so forth. But anyway, howsoever that may be, let's move on to, by the way, this is like, I forgot what sections, I guess it's right in front of me. We're covering 7.1, 2, and 3, and really what I just showed you there in blue is kind of 7.3's discussion, the fact that this can be done using calculus. So if it can be done using calculus, then do you agree that since moving down this list is taken an integral, does it make sense you could actually find the moment right now just from 1680 minus 8.75x squared? Why don't we try it? What's the integral of 1680? 1680x. What's the integral of 8.75x squared?
2.92 x to the 30.
Yeah, the x squared grows a cubed, right? And then you got to divide by 3. So you have 8.75 divided by 3, which if you do divide it, you get a rounded answer. You could multiply, since 0.75 is quarters, you could multiply the top and the bottom by 4, and you'd have something twelfths for that. I don't know what it is, but if you wanted it to be less weird looking, and you didn't want to, because it gives you a decimal that repeats, then you can't really write it down. Or on your calculator, you could say, convert this to a fraction for me, and I just did that, and it said 35/12. So that'd be maybe a nicer way to write that down. I'm not going to write it differently because I want you to see the calculus in my notes here if you look back at it later. What's missing though? Plus a constant. And of course, we might think, well, we now realize that's kind of important. It isn't just like any old constant. And ultimately, m of 0, in other words, when x is 0, don't these two terms go away because they have 0 in them? So the moment when x is 0 is what c is. But I find myself thinking, what's the moment at 0? Like, I don't know that. How am I supposed to know that? Well, let's just let that hang for a little bit. Let's go see if we can actually, do this the long way, or do this drawing a picture and so forth. What would the moment equation be, if you will, manually? I'm going to copy this free body diagram down so we can see it where we need it. Oh, fail. Yes. So what are the sum of the moments around point A? Well, I got M over there. It's already a moment. Doesn't have to be multiplied by anything. That's why it's very important to draw that as like a curve so you understand. And it's positive. I always like to write a positive number first so I don't get a negative and an equal sign and kind of lose that just in my lack of ability to read my own handwriting. So I always kind of like to write the positive one first. So there's that one. And then there's the shear, which is going the other direction clockwise. So it'll be negative, and its distance away is x. That starts to look like v of x instead of v times x. I'm going to write v times x. And then I've also, in the same direction, got that 8.75x squared. And how far is it away? Well, again, this is it. So that's why I wrote 2/3 x in there earlier, because if I didn't write that in there, I got to think a little harder, right? That's not that obvious. So whatever x is, 2/3 of that. And that's it. That's all the forces. And so if I left m on this side and added the other, well, negative numbers to the other side, they'd become positive. So m would be equal to bx let's see, 2/3 times 8.75. Maybe we'll get lucky and that'll clean that mess up. I have a feeling it won't, but I'm just gonna cheat on my calculator and say 8.75 times 2 divided by 3. I get a crazy decimal. I say convert it to a fraction for me, and I got 35/6. So that is plus 35/6 cubed. I got a cubed equation. Did you notice our shear equation back here? Should have boxed that because that's going to stand out. Our shear equation was squared here. And so we're going to move up a dimension when we take an integral. So it went from squared to cubed. In a sense, that's not a coincidence. Our linear equation was x. Our shear equation was squared. Our moment equation is cubed. What's that?
It's always like that.
Yeah. It's always like that. And so like, where's the constant? You know what I'm saying? Like, because remember, this method is not using calculus. It's like, well, maybe the constant is 0 back here, right? Is it possible that moment at 0 could be 0? That's possible. Yeah, but maybe a constant will pop up when we put v in, because remember, v is, we don't really want the equation to be in terms of v's and x's. We'd really like v gone. And since v from earlier was 1680 minus 8.75x squared.
Everything's getting excess, so it shouldn't have constant.
Yeah, but everything's getting an x. You're exactly right. So 1680 times x would be 1680x. 8.75x squared times another x would be 8.75x cubed. And then I've got my 35/6 x cubed. So hey, look, I got two like terms. And so m would be 1680x. And let's see, I guess 8.75 a minute ago was 35/12. So I think I actually end up with minus 8.75. I don't know. I'm just going to double check. I'm going to say 35/6 minus 8.75. I got that same word decimal I got before. When I converted it to a fraction, I got 35/12. Negative 35/12 x cubed. And by the way, that is 8.75. And so I find myself looking back at the calculus we just did, going, hey, that's the same thing. I think, is it? No, it isn't. Because this was 8.75 divided by 3 x cubed, wasn't it? Whereas this is, maybe it is an 8.75. Maybe I just did that in my head and that's not true.
It equals the same.
Yeah, I shouldn't have said that. I don't think that's true.
The 8.75 divided by 3 does equal 35/12.
Yeah, I just got excited. Like this number right here is 35/12. So they're the same. And so it turned out, well, the constant was 0. So in a sense, I got kind of lucky. Like if I had done calculus, I wouldn't have known what to do because I'm not good enough at this yet. I haven't practiced enough. And so, you know, I don't know how I would have done that, but it turned out the constant was 0. So we got kind of lucky. So now we got our moment equation. And calculus still worked. And so I'll make a note of that over here, maybe in red. When we took the integral of v, we actually got n. Or if you took the derivative of n, then you'd get v. And so that's just kind of a cool check. For your knowledge's sake, I'd prefer you just do this the way we did it in blue, and then use calculus to kind of check your work when you're done, because that'll make you smarter. It'll make this go into your head more deeply, because in reality, the calculus represents a cheat code, so to speak. Like it's a sort of, except for that constant was kind of a problem, right? But it kind of represented a cheat code.
Take your weight formula, take the integral of it, and then integral again. It'll be wrong. You don't have your constant from
That's right.
shear force. Unless you remember to put it in. You'd be skipping one step.
Exactly. So again, just for the fun of it, and this actually will be fun, I wonder what that moment max would be. Well, remember in calculus, if you take the derivative of something and set it equal to 0, so it's like I got to take the derivative of that green equation, but then it's like, well, no, I don't. It's already did it. It's v. And so I'm really taking this v of x equation, 1680 minus 8.75 x squared, and setting it equal to 0, right? That'll be the x where the maximum is. But didn't we just do that a minute ago? Didn't we just do that a second ago?
13 point something.
Isn't it right there? That's actually why I stuck that in there earlier. We saw that the other day, and it turns out to always be true. The minimum shear, when shear is 0, that's where the maximum moment will be. Isn't that kind of weird? And notice it's weird in this case because it's not even in the middle. Yesterday or the other day we had, I forgot what size the beam was, but if it was 24 feet, then the maximum moment would have been right in the middle at 12. Well, now it's not. It's not in the middle. It's in some weird location. So if you take the time on the shear graph to actually calculate where that graph crossed the x-axis, then you'll already know where the maximum is, which means you could actually come down here then and just say, since you already know that, what did we say it was, 13.86, 13.86. Since you know that it's at x is 13.86, then you could go back and say, okay, well, what's the moment when you stick in 13.86? 1680 times 13.86 minus 35/12 times 13.86, except for that's cubed. And now I already know the maximum moment. Now, again, I want to look at the graph because we just saw a minute ago that didn't work for a parabola. And so, you know, is this really right? Like I need to look at a graph of this to kind of check it. But at least if the graph isn't weird, 1680 times 13.86 minus 35 divided by 12 times 13.86 raised to the third power, I got 15,519.1.
So where is this moment? Is this moment around A? Because I thought the maximum moment would be 2/3 of the way over 16, but it's not.
Yeah, isn't that interesting? Like you thought maybe it'd be 2/3 of the way over because that's kind of where
It's the
all
longest
the
lever.
forces kind of coalesced in that. But no, oddly, it isn't 2/3 of the way over, isn't it? It's not
Yeah.
weird. It's kind of in a weird location.
Well, so I'm wondering where our frame is now, like moment as opposed to
Yeah, and so what we're really talking about here is the desire to rotate at that location. So if you went to each location, what's its desire to rotate right there? What about here? What about here? So it's not so much at a point, it's just kind of like what's happening at that spot.
We have to think
And
about it
basically
back
at
in that triangle.
13.86, that's where you get the worst. And so again, the main thing then is to take that 15,500 and go look in that table I showed you the other day and say, okay, now what beam can not rip from that number right there? So we have two things to look up. I don't think, pretty sure I didn't save that in here and should have. That would be awesome. Let me see if I did put it in here. I don't think I did. Nope, it's too bad. But let's take a look at a quick graph. Again, what I'm going to do is just cheat on my calculator to get the graph of that equation. So of course, this is kind of the equation you want to box because this is what all the work was. So if I go down there and make a graph of it, I would need to have 24 on it and 0. I don't know right now, is there going to be negative answers to this? Because remember, negative and positive moment kind of mean they both matter. And we'll talk about that a little bit more in a second. But if I graph this 1680x,
And one window has to be over 15,000.
so I got a graph that started, you tell me if you got the same thing, It started right here and it came down right there and it was above the entire time. But in terms of locating it, does it make sense if I did this right? That 15,500 should be the top. So what I saw is the graph took off and I couldn't see the top. So I'm going in the window and I'm saying, well, if I got this right, then I should be able to set this to 15,600 and I should perfectly see it. So window, Y max, 15,600, set it to 16,000, whatever. A graph, I should see the top. And remember, you can cheat in your calculator to find that location. And you should be able to see, and it's kind of important to notice this, that it's not a parabola. You can totally tell by looking at it. You should, again, have this in your graphing calculator. But it actually peaks kind of like way over to the right. It's clearly not in the center. And therefore, it kind of comes down really steeply at the end.
So our parameter is 0 to 24 again, right?
Yeah. And so indeed, that is 13.86. Now that I look at the graph, I can tell that my calculus actually worked here because that really was a maximum point. Remember, it could have been a minimum. Now, as a side note, your conventions, take a look at this. You don't need to know this deeply, but the conventions of sign. You see that, what's called a positive moment? Do you agree this entire beam, because all the weight was on top, look up here for just a second. No matter where you are, the beam's trying to bend down, right? It's always bending down. We'll see what that shows right there. If you push up this way and you push up this way, isn't the beam trying to curve down like our beam is? And what do they say? That's positive. Well, our beam has weight on it the whole time, so every place you go, it's curving down. We'll notice the graph shows positive Y values every single place you go, does it not? So there is no negative moments here. So in a sense, it sort of makes sense that the graph is there. Also notice, oh yeah, look, at time 0 or at distance 0, when X is 0, the moment really was 0 on the graph. I don't know if I could have known that any other way, at least with what I know right now. So it's actually saying at the beginning of the beam, there's no moment, no desire to rotate at all. That makes sense because it's supported over there, right? And there's no moment over here, it's supported over there. But out there, not in the middle, but to the right of the middle, I get this maximum spot. So if I said X over here and M over here, and then I had this labeled at 15,519, that would be a complete free body diagram, or I'm sorry, a complete moment diagram now, because you got to learn from it. The 15,519's got to be on there. That's the only reason you made this graph in the first place. And so does the 13.86, I think. So it's kind of cool that calculus and the graph are saying the same thing.
How would you like 16,000?
Incidentally, I didn't show you this the other day, but a shear moment diagram is one of the options in BC Calc. I can actually just spec the whole beam out and see that all the percentages are passing. And then I can say, click, I need a free body, or I need a shear moment diagram, and it draws what we just drew and labels the important parts, just like this. I mean, that's kind of nice that it does that. Now, as I said before, I think you need to sort of go back through this, and I'm going pretty slow in here because I really want you to take this in, and maybe some of you actually really feel like you have this right now, but go slowly through this so that you kind of feel like you can do it. Recognize from calculus if you got it wrong.
When's the test over all this?
I'm thinking next week is the last week. I'm thinking I'm teaching, we're going to review on Tuesday. So after today, there's really nothing else you need to learn. But let's spend a little time together just talking over what's gone on, because we feel like we've learned a lot since then. I don't know about you, but I already forgot what was before this and trusses. It's like I kind of need to relook at all that stuff and make sure I know what I'm talking about. And then I'll probably just email you the test again. Let's talk about that right now since you brought it up. I'm thinking, in a sense, the test is Thursday. Like I'll email it to you Thursday. Gives you another day to study, but I'm sort of flexible.
And then is the reviews, you opened all the reviews.
Yep, it's already in there, so you can start playing with it anytime. So basically you just owe me if you have homework I have all the homework in except for Ian's. So double check and make sure that's all.
So the last homework I saw,
Okay.
there was one that is all red, said cables question mark.
The 7 point something.
It's the last homework set that we had.
Oh, yeah, that was like if we get to it, which I don't think we're going to, so. I had a question mark on it. I always kind of wish we do, but we never do. Cool, so let's see, I'm trying to show what to show you next. So there's no end to how cool these get. If you start adding, these two loads I just put on these are fairly uniform, relatively simple and common loads. Those are common load designs, but there's all kinds of crazy stuff. Like what happens if I came back to the same thing, but I just put 1 point load on it? Like there's that beam sitting there and it has this triangular load. But what if I just came over here and said, let's put 1,000 pounds right there? Does it make sense? That's going to really make the shear weird. Like you're moving along as X goes from 1 to 2 to 3 to 4. And then suddenly, bam, now all of a sudden 1,000 shows up on this diagram right here. What's going to happen there? Like, isn't it going to tweak the graph? Like as we moved across this, nothing changed. It stayed the same the whole time. And now all of a sudden, bam, there's a point load. Like what happens then? And so you can
That make it easier, right?
really nerd out on this. It's kind of neat, but
Because our X is solved for at that point. So it's not like we have to make an equation at that point. We just solve for it.
well, you still have to find the maximum shear. And you just made it worse by adding something else to the problem.
That's
Are you
a
adding it
whole
on top of
new force
Yeah.
on it, not.
You're adding it on top of the force that's already
the
there.
top of the
Yeah,
triangular
so
force?
Yeah,
it's
on
added
top of the
onto-
triangular force.
I thought you were just adding it and that's it, like no triangle.
Oh,
I
that
was
would
like,
change the whole momentum.
that's easy, right?
That's exactly right. It would be very easy if you
Okay.
just had one single force. And so we actually started out with something kind of challenging because it had millions of forces on it. So I'm actually trying to decide what to show you next because we have time for one more. I'm relatively sure I'll show you.
So Doug, I guess if you added that on top of the triangular force, would you recreate your free body diagram, but add a V right on top of the A?
Kind of, yeah.
So you'd like have a whole new equation. You'd have
Well, you have
two.
to start from the momentum because it would switch momentum as well on A and B.
Take a look at this one. Tell me what you think about that. So your first reaction should be, sweet, they're all equal. We already did this. This is going to be easy. I can do this myself now. However, look a little closer.
Oh, the points, no. Yeah, A and B are,
How is it supported?
so you have one that's gonna create force.
I think this is what you're looking at. I don't
A, B, and then you have the whatever 600 feet of the ring.
think of this as a freebie in the sense that, like, this isn't on a test. This isn't on your homework.
So it has two shoes.
This is harder, but
Yeah.
at least it will open the door to, I don't know, a bit more of a complicated world, because notice what's happening here is it's being supported, well, cantilevered. So the beam is, and I didn't write this out super clearly, but the beam is 32 feet long, but the right 8 feet of it is actually cantilevered out. And by the way, this is actually super common when I design decks for people all the time. There's a beam here and it's usually like anchored to the house over here. And then out here somewhere, you put a beam underneath it to support it. And so this beam is sitting on a post, and then up here is the railing and stuff that, people are basically living up here on the deck. But a chunk of that usually sticks out because it just looks better that way. And so something being cantilevered is kind of interesting. So I just show you this to kind of increase your power of mind, because it makes a really kind of a fascinating free body diagram. So notice I made the load kind of simple. So let's see if we can do this kind of really fast. We have a little less than half an hour, so we don't have to go terribly fast, but let's see. Well, the first thing we got to do is establish what engineers call reactions. So I'm going to go ahead and say that. And that really just means what are the forces of A and B that are going to counteract that 438 pounds per foot? So if I say 438, notice because this is a rectangular load, pounds per foot times 32 feet, then that's going to give me the sum force of all the weight up there. And so that is 438 times 32, that is 14,016 pounds. And notice in this case, because it's rectangular, we know it's exactly in the middle. So that isn't that hard to locate. So it's okay. I can think of this as a beam that is supported here at A. I'll call it the force of A. And here at B. And right in the center, I've got 14,016 pounds. Again, does that represent a nice, clean, free body diagram in the sense that that's all the forces that are on this thing? And so I can't do a sum of the forces in Y because that would be something we'll call later an indeterminate equation. Because as long as force of A and force of B add up to 14,016, then we're good in Y. But as you know, if I do a sum of the moments around whatever, A or B, doesn't make any difference. Let's do it around B this time, just because we're always doing the other one. If I did it around B, then I would have, let's see, the force of A would be pushing negatively. The force of 1416 would be positive. How far is it away? How far is it away? Notice I didn't draw that in, but it's like this is 8 feet over here. And this would be in the middle at 16 feet. So wouldn't it be 8 feet? So isn't this distance right here 8 feet from B? And then I have the force of A, but it's causing clockwise rotation, and it would be, well, 32 minus 8, which is 24 feet away. Because I know that this 1416 is in the middle, which means it's 16 feet over here and 16 feet over here. And since this much of it is 8, then there must also be 8 there.
Wait, if you said there's B is already over 8.
Oh, no.
So-
Oh,
So basically, this distance is 8, this distance is 8, and this distance is 16. Does that make sense? So, okay, cool. That gives me a way to find the force of A. So if I add force of A times 24, basically I've taken 1416 times 8 and then dividing by 24, and I got 4672. That'd be pounds, of course. And so now I could switch to the sum of the forces in Y. And since I have 4672 pushing up, last time I didn't bother to write this down so clearly. And I have 14,016 pushing down, and I have force of B pushing up. I get 9344. So do you see why force, just from looking at the picture, do you see why force of B would be doing more work here? Let's see, I wonder if this is true. Let's see, B, I'm just thinking out loud here. Wouldn't B have to carry all of this weight, right? All by itself. And then wouldn't it have to carry half of the weight on the other side? So it'd be like if I found the center right here, it'd have to carry all this weight. And then A would carry this weight over here. Does that make sense? Like that's how it would kind of split up. So I wonder, since this distance is 24 feet on this other side, then wouldn't this be 12 and this is 12? So if I took 20 times 438, would that give me 9344? I don't think it does, by the way, but it might.
You said again, if you took 20 divided by 30.
Well, since we're thinking this has basically it's in charge of 20 feet of the beam.
Right.
And since 438 pounds per foot, I was thinking, well, maybe 438 times 20 would be 93, 94, but it actually isn't, oddly. And the reason for that is when you push down over here, does it make sense that's actually helping lift over here? Teeter-totter-ish. So it's not quite that simple. So cantilevers are really kind of interesting. Does it make sense if you put a bunch of weight over here, this side of the beam would actually bow up, which would actually be negative moment. So that's going to happen here. Like we're going to have some negative moment. When you have a beam that's not supported on the ends, it isn't just going to bend down. It actually can bend up in places. Actually, what's realistically going to happen with this beam is it's going to go like this. Let's see, I think, is that right? I don't know. You got to think about that.
So F of A is the wrong way then. F of A needs to be facing down the arrow.
Maybe. But again, that should take care of itself. Well, anyway, now that we've got that, then we basically have the power to draw a free body diagram now, because we have all the forces. Since we calculate all the reactions, then we kind of know what's going on.
I guess it wouldn't be, because it would be negative already, right? We already found force of A.
Yeah, we know the force of A, so they both were positive. At least we think so. Well, let's go down here. Let's just start shear right now and see what happens. So again, because we're finding the shear as a function of X, because we need to know the shear everywhere in order to determine the maximum. Force of A was 46.72. Up here, we're kind of lucky. Since it's rectangular again, we can say this is 438 just times X. If this distance is X, and it's right in the center of that, half of X over there. We said shear was going down. We said moment was going up. But an important addition to this, I think we have everything on here, but an important addition to this is, does it make sense if we make it all the way over to, as soon as X makes it to 24, take a look at this picture up here. Since this distance right here is 24 feet, does it make sense if X makes it to 24, then all of a sudden there needs to appear this magic force of B? So it's like, what? How are we supposed to account for that? Well, we account for it by saying this picture that I drew here, it only works for X between 24 and 0. We're actually going to have a totally separate equation. We're going to have a separate drawing for 24 to 32. So the sum of the forces in Y would be 46.72 going up, V going down, and 438X going down. And that's all the vertical forces, so that would be equal to 0. So then we can say shear is equal to, add it to the other side, 46.72 minus 438X. And again, I'm going to add this over here. As long as X is between 24 and 0 anyway, this is our shear equation.
One of the shear equations?
What's that?
One of the shear equations?
One of them. Because as soon as we get to that other force, then isn't that suddenly going to be there? Like it basically isn't there, it isn't there, it isn't there. And all of a sudden you hit 24, bam, there's this, what size was it? There's this 344 pound force that's suddenly a part of the shear equation. You see what I'm saying? So it's like, you can't do this with one equation. That's what it comes down to.
then are they just additive? Like, do we add one to the other?
Good question. No is the answer to that. I'll show you. Okay, so well, let's do kind of the other part of this then. Hopefully we'll have time. So if I redraw this shear, then I'll draw it a little longer just so it kind of looks like it went longer. No different, shear goes down, moment goes up. I don't really need the moment drawn in there if I'm just doing shear, but and I've got 46.72 pushing up here. And then I've also got 93.44 pushing up here. So, as I said, it's actually important to point out, oh yeah, this is actually for when X is bigger than 24 and less than 32, since the beam was 32 long. Are you okay with that? So I have to say it's bigger than 24, otherwise the 93.44 isn't there. Do you see what I'm saying? Now, it hasn't changed. X is still this distance all the way to wherever we are. We still have in the middle of that 438X pushing down. So nothing has really changed except for when we make our shear calculation. I'm just going to have that 93.44 in it. And so let's see what that looks like. So I would say this time the sum of the forces in Y equal 46.72 up, but then also 93.44 up. V going down and 438X going down. So that's all it added. Now, of course, 46.72 plus 93.44 is the sum total, that 1416 number we had earlier, right? It's that number, 1416. So in the end, my shear equation becomes, if I add V to the other side, it becomes 1416 minus 438X. And again, important to note that this is only true because it's a totally different equation. By the way, what is different about the equation? Aren't they both lines? But what's different about them? The y-intercept. They both have exactly the same slope, do they not? Their slope is negative 438x, but one has a y-intercept of 46.72 and the other has a y-intercept of 14.16. Isn't that kind of interesting? So no, you actually just have to graph them separately. So watch this. Let's do it in Desmos. Maybe we won't make it to the moment. I don't really want to keep you guys late. So
Desmos has to think of pain in the butt.
is it hurting you?
Kind of. Well, I remember we talked about how you should be able to put like cross section that we click on it. I don't know why it's not working really well. I think it's because it's so steep and then X is just a straight line that it's kind of like blending together a little bit.
Yeah.
We'll get that spot going for it.
Wish I could copy 46.70. Gosh, it's crazy. 2 minus 438x. Incidentally, just because it's kind of fun, notice what I typed there. I called it V1. Have you ever done that before? This is kind of a cool place to do it. And then I'm on my screen hitting V, but then there's this little A over B button in the lower left-hand corner, A over B. So I can call them both shear that way. I don't want to rename, I don't want to call them Y. I'd like somebody to kind of know what I'm doing. So that's just kind of cool. 406 minus 438. No 38. Now, notice the y-intercepts on these things. One so this lives, the whole thing lives from 0 to 32. So if I go to that wrench up there, I can say, I want this thing to live from 0 to 32. And for Y values, I'm not exactly sure what to put. But the Y-intercept of one of them is 14,000. So my max seems like maybe 15,000 would be good.
You missed the 2. Okay, next.
Thank you. Hitting those, they start showing up. Anyway, it gives me something to start with. And then I'd like to kind of come back and limit these because all I'm seeing is 2 parallel lines. Remember, we said this one lives and we use those brackets. And we said this lives from 0 less than X less than 24, was it? It's too bad. Thing. So that's what the shear diagram looks like, at least for 0 to 24. And then it suddenly, and watch what happens when I add the same thing for this one. Then I move from 24 less than X. 2 didn't show up again. Of course it didn't. 24 less than X less than 32. 2 didn't show up again. Of course it did. Now, so what actually happens is the shear just in an instant jumps to a totally different number. That's what it comes down to. Do you agree without looking particularly at the graph? If I look down here at the bottom of this, notice that is like, what is that, 5,700 or something like that, negative 5,700. And maybe you're sitting there at X is 23.9. And then you jump to 24.1 and suddenly, bam, it's positive and it's up by 4,000. Like that's exactly what happens.
So Doug, is that on the left side of B or the right side of B? Like, are we thinking of it as like a point?
Yeah, actually they have to connect. And so there's actually a vertical line between those two, as it turns out. So actually you have to go back in here and say X equals 24, 4. And then, I have to figure out where those cross, but does it make sense if I went one step further and said, okay, this is between, let's see, we said like negative, what do we say, 4,700 or something like that? I'm guessing, but you should be able to do the math on this, right? I haven't stopped to think about that yet, but notice I'm choosing Y this time. And then the Y max looks like 3,500 or something like that. Of course, the other 0 didn't show up. So it looks like 3,500 was pretty good. It looks like this is more like 5,900 or something. So that's close enough for now, but like actually that's what the shear diagram looks like. Now again, why do we draw this? Because the max is not obvious. Is that positive red maximum over there bigger than the negative red maximum? You understand what I mean by that? I can't poke at this, but
The red maximum is bigger than the blue maximum.
yeah, so the blue maximum is lower than red, so I sort of don't have to worry about the shear over there. But then you have like a positive on the left side of that red graph that looks like it's under 5,000. Do you agree with that? But then the bottom side is over 5,000. So it's like, well, didn't we just say negative 5,900? So there's our max. Our max shear is roughly negative 5,900. Now, of course, I could solve that, right? What would I do? Well, I'd put 24 for X into the red graph, and that would tell me what Y was, right? And it's not like I had to guess lamely like I was just guessing, but like literally that is the shear diagram.
I was trying to do that too. Do you do F of V1 equals 24? Is that how you would say it this much? I like,
Oh, to get it to find the intersection?
Yeah.
Actually, in the interest of time, let me show you. I already Desmos this at a much higher level.
There you go. How do you get it? I'll figure it. It's probably the computer.
Let's see. I can't remember if that was intersections because I drew all three of the graphs. Then it would find those intersections. So all I did is click on all of them and then just screen capture that. So that's my complete shear diagram. So notice it's actually 5840, not 5900. Maybe I'll need that later. Remember that 0? Didn't we say where the shear was 0 was where the maximum moment was, 10.67? Take a look at the moment diagram. Looks like my labels moved all around, so it doesn't look right. But look at that crazy moment diagram. What do you have there? Well, you have, let's see, what would this be? It's a parabola, right? Because our shear was x to the first power. So when I take the integral, I mean x squared. So it's like I got this parabola over here, but then as soon as I hit there, bam, it started on a totally different parabola. So it is really two different graphs, but it's actually kind of cool that they connected down here. So again, I'm looking for the maximum number, and notice it's right there. And what do you notice about where? What do you notice about where that is? Hey, it's at the same exact spot where the shear was 0. So in this case, my takeaway, of course, would be, bam, there's my maximum shear. Bam, there's my, maximum shear and maximum moment. So
that second diagram doesn't work for the second max, because the max moment on the other one is going to be 8 feet to the right, correct? So that's going to be at 32, but at 32, it's saying it's got 0 moment. That doesn't make sense, right?
yeah, so at 21.33, 21 1/3, it actually has no moment at all. There's like no desire for it to break there. Now it has shear at that point, so it's not like you can have no beam there.
But what about 32? What about the end of the cantilever? There should be a drastic moment to go downward, right? So why is it saying there's 0 moment?
Yeah, I see what you're saying. That's a good question. I mean, it is bending down, but it's basically getting less and less as you move out there, I think is the idea. Because notice it's a negative moment here, and it just keeps getting smaller and smaller and smaller and smaller until you get to the end, and there's actually none.
Right.
I guess that makes
24 is where
sense
the
because
max shear
nothing
was.
is pushing on it. Mhm.
So it's working for one, but the other isn't working.
Yeah, it's interesting, isn't it? It's also kind of cool to draw them together, because here's where you can kind of see, hey, look at that. That lines up. And this kind of maximum negative moment, if you will. And again, notice negative moment is really interesting because that's actually saying it's bending up in there. Bending upwards through that section. At least I think that's what it's saying. Actually, it's bending upwards everywhere in here. It's bending upwards from there on. So it's kind of like, I think what it's saying is here's the beam is bending downwards to here. And then it's bending upwards to there. I think that's what it's saying.
Oh, that makes sense too.
It actually does make sense because remember you have force out here pushing this side down, but there's nothing to support it. So it really would create that S kind of a shape. So that actually is right. That was bothering me until just now when I drew it. So it's concave up over here and concave down from then on. So that's kind of fascinating that we can learn all of that from that graph. The actual shape of the beam would actually be in is an S in this case. That's just crazy, isn't it? So I don't want to keep you guys. Otherwise, I would do the moment calculation on that too, so we could actually get that equation. But I think I'll finish it and post it so at least you guys could see it. Again, don't look at that over spring break or something. I wanted you to see it, but don't clutter up your brain.
Maybe.
I've fallen off. I'm trying to get back on.
What are you been on for years?
Dude, and I was 8.
New year. You know what I mean? So I went at like, well, 6 the other day. That's the same. Experience level. Well, I don't know, wait, so it's just about like, I know, it is. Thanks, Doug.
You bet. Good to hang out with you guys.
Yeah, if I drop the wrong one, that's okay. I deserve to die. I always get those things all the time. So.